So I will try to give a really brief introduction about this dimension reduction. If you have lots of predictors and if you want to use some of them, or if your n, which is number of observation, is smaller than or close to p-values, you may want to use some dimension reduction methods. And let's move to the next page. Here is the general schema in here. Now what we are doing is that we try to explore a class of approaches that transform the predictors. Here are my predictors in here. I have p number of predictors. And we are kind of trying to transform these guys and then fit a least squares model using that transformed variables in here. So this is my new variable. This is the transformed version of your predictors in here. And please keep in mind that the main point in dimension reduction is that you have less number of dimensions in here. M is smaller than P, and here is your new Y. Please remember that we were writing something like Y equals beta 0 plus beta 1 x1 plus to the beta p xp. And in here, instead of that one, we have Y equals theta 0. And now we have again our estimations, our parameters in here. I mean, these are not estimation now. There are parameters in here related to your transformed variables. And when you see that one, if you want to write them in an example, let's say you have P as 4 and M as 2. Now your dimension is going to be 2 as predictors in here. And we are going to just transform that X values depending on these parameters in here, which are phi's. And now we are able to write our Y equals theta 0 plus theta 1 z1 plus theta 2 z2. Okay, so please keep in mind that we are not selecting variables in here. It is not like subset selection or regularization methods. We are just transforming them, and that means we are still using all our variables or predictors in here in dimension reduction methods. So instead of estimating p plus 1 coefficients, which are beta 0, beta 1 to beta p, we are trying to estimate m plus 1 coefficients. These are smaller number than that guys in here. We have less of them. And yeah, we know that. Now we have two steps of all dimension reduction procedures. These are our main steps. The transformed predictors Z1 to Zm are obtained, and the model is fit using these M predictors in here. Okay, so how can we do that? What kind of methods we can use in here? And the principal component analysis is one of the examples that we can use for dimension reduction. In this example, I just got this one from ISLR book. It is ISI Introduction to Statistical Learning with R book. And you see that they are trying to see the population versus advertisement spending in here. And now you see that this green line is our first principal component, and that blue line is our second principal component, okay? And now we are kind of trying to explain this data by looking at these principal components in here. And this part is just self-study for you guys, and you can just check out for that principal component analysis in the book of in the ISLR book of statistical learning in here. Okay, and I also want to say something about that high dimensional data. High dimensional means that your p-values, that means your predictors, are greater than your number of observations. Okay, now your data is kind of white. And so in here, if you have that high dimensional data, Classical approaches such as least squares, linear regression are not appropriate anymore. Please keep in mind that. If your p-value is greater than n or close to n, a simple least squares regression line is too flexible and it's going to overfit your data in here. Okay, so when you look at this graph on the left, you will see the least squares regression in the low dimension settings in here. Okay, and in the right you see that we have least squares regression with n equals 2 observations and 2 parameters to be estimated, an intercept and a coefficient in here. And so when you just check out for these two values, they're kind of not enough to fit your model in here. And when you have a very small change in your data and your regression line is not going to be appropriate for your test variable, for example, in here, okay? So this line is too flexible to be used for your model. But if you have this kind of data, I mean the low dimensional data in here, it's okay to use least squares. Please keep in mind that. This is another way that you should use dimension reduction in this kind of setting sometimes. And let's see, there is also one example in here. When we are fitting a model, we are kind of looking for the goodness of fit test, okay? We want to see how our model is good. If you are familiar with statistical tests, you will see that we use lots of R-squares in statistical tests, or even for some machine learning methods in here. If you just examine only the R-squares in your models, or if you just check out for the training test MSE in here, you will see that your R-square is getting higher when you have more variables in here. And you will think that, oh, my model is great and I can use that model with that much variables in here. You can use lots of predictor variables in these settings if you just use R-square, okay? And this is also, we have the similar comments also for this graph in here. If you solely look for training MSE, you will see that when you add predictors onto your model, you will see that your training MSE is getting lower and lower for each variables. Okay, so you can just say that the model with greatest number of variables is the best for me, but this cannot be true for you. Okay, so this indicates the importance of applying extra care when analyzing the data sets with a large number of variables, and of always evaluating model performance on an independent test data sets. This kind of what we are saying in cross-validation. So when you just only look for R-square or maybe AIC values, BIC values, if you are familiar with them, or when you just look out for training MSE, it's not going to be enough for you. If you just look for them, you will just add number of variables onto your model, and then you will think that, this is my best model. But if you just work with an independent data, you should also see the test MSE. You will see that when you add your variables, your test MSE may be getting higher and higher, okay? And then you should find an optimal point in here, which train your model with training the test, but also that model should work well in your test data set too, okay? So please keep in mind that you should be checking for your test MSE too in this kind of settings, okay? So yeah, I just write that, watch out the model performance on an independent test set in here. And here are the references I used to prepare some part of this video.